Hello student, I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss trends in stability of higher oxidation state. Last class I have discussed oxidation states of transition elements. Also I discussed trends in the standard electrode potential. Now I am going to discuss trends in stability of higher oxidation states. The stable halides of 3D series of transition metals I am going to discuss. Stable halides of 3D series of transition metals. The highest oxidation number are achieved in titanium X4 means tetrahalides. X means halide. TiX4 tetrahalides. The highest oxidation number are achieved in titanium X4 means tetrahalides. VF5 vanadium pentafluoride and chromium hexafluoride. These are the examples. The +7 state for manganese is not represented in simple halides, but MnO3F is known, and beyond Mn no metal has a trihalide except FeX3. Again you listen carefully. +7 state for manganese is not represented in simple halides, but MnO3F is known, and beyond Mn means manganese no metal has a trihalide except FeX3. This is an exception. Except FeX3 and COF3, both are in exception. The ability of fluorine to stabilize the highest oxidation state is due to either higher lattice energy, as in the case of COF3. Again I am telling you, this is an important point. The ability of fluorine to stabilize the highest oxidation state is due to either higher lattice energy, as in case of COF3, or higher bond enthalpy terms for the higher covalent compounds, as for example VF5 and CrF6. Although vanadium fifth is represented only by VF5, the other halides, however, undergo hydrolysis to give oxohalides means VOX3. Another feature of fluorides is their instability in a low oxidation state. Question is asked. This is another feature. Another feature of fluorides is their instability in low oxidation states. Example VX2, where X is equal to chlorine, bromine or iodine. And the same applies to CuX. All are lower oxidation state. On the other hand, all Cu2 plus halides are known except iodide. Exception is iodide. Again you listen, all Cu2 plus halide are known, except exception is iodide. In this case, Cu2 plus oxidizes iodide ion to iodine, means 2Cu2 plus 4I, 2Cu2 plus 4I minus, that gives Cu2I2, this is a solid, plus iodine. However, many copper second compounds are unstable in aqueous solution and undergo disproportionation. 2Cu1 plus, it gives Cu2 plus Cu, means zero oxidation state. The stability of copper 2 plus rather than copper 1 plus is due to the much more negative, means delta H hydration. More negative is due to the negative delta H value of Cu2 plus. Again I am telling you, the stability of Cu2 plus rather than Cu1 plus is due to the much more negative of delta H hydration of Cu2 plus than Cu plus, means hydration value is responsible for stability of Cu2 plus. Very negative, more negative value of delta H hydration of Cu2 plus, which are more than this negative value. I am talking about hydration, delta H hydration of Cu2 plus, which is more than compensates for the second ionization enthalpy of copper. The ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. The ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. Now I am talking about the oxides of 3D metals. Oxides of 3D metals. Then this ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. The highest oxidation number in the oxides coincide with the group number and is attained in Sc2O3, scandium trioxide, to Mn2O7, starting from scandium trioxide to Mn2O7, manganese heptaoxide. Beyond group 7, no higher oxides of ferrous above Fe2O3 are known. Listen here, beyond group 7, no higher oxides of Fe above Fe2O3 are known. Although ferrate 6 means FeO4 2 minus. Then here I told beyond group 7 no higher oxides of Fe above Fe2O3 are known, although ferrate are formed in alkaline media, but they readily decomposes to Fe2O3 and O2. Besides the oxides, oxocation, not only oxides, even the oxocations. Besides the oxides, oxocations stabilizes vanadium, means V5, as VO2 1 plus, V4 as VO2 2 plus, and titanium 4th as titanium oxide 2 plus. Okay, means besides oxides, oxocations stabilizes vanadium as VO2 1 plus, V4th vanadium V5 as VO2 1 plus, vanadium 4 as VO2 2 plus, and titanium 4th as TiO 2 plus. The ability of oxygen to stabilize these high oxidation state exceeds that of fluorine. Very, very important point. The ability of oxygen to stabilize these high oxidation state exceeds that of fluorine. Means oxygen stabilizes more than fluorine. Correct? You know that fluorine has highest electronegative in whole periodic table. Despite that, the ability of oxygen to stabilize these high oxidation states exceeds that of fluorine. Thus the highest manganese fluoride is MnF4. The highest Mn means manganese fluoride. Highest Mn fluoride is MnF4, whereas the highest oxide is Mn2O7. Highest manganese fluoride is MnF4, only F4, 4 oxidation state, whereas the highest oxide is Mn2O7, means Mn has +7 oxidation state. The ability of oxygen to form multiple bonds in metals. The ability of oxygen to form multiple bonds in metals explains its superiority in the covalent oxide. Mn2O7, each Mn is tetrahedrally surrounded by oxygens including MnO-Mn bridge. In Mn2O7, 2 Mn is there. Then each Mn is tetrahedrally surrounded by oxygens including a MnO-Mn bridge. The tetrahedral MO4 N power N minus, you can tell, MO4 N minus maybe N maybe 1 2 3 like that way. Then here the tetrahedral MO4 N minus ions are known for vanadium 5th, chromium 6th, manganese 5th, manganese 6th, and manganese 7. Tetrahedral structure I am talking. The tetrahedral MO4 N minus ions are known for vanadium 5, chromium 6, manganese 5th, manganese 6, manganese 7. Okay, this I have discussed here oxides of 3D metals and discussed trends in stability of higher oxidation state in case of halides of 3D metals or oxides of 3D metals. Now one question is asked, I want to discuss that question. How would you account for the increasing oxidizing power in the series VO2 1 plus is less than Cr2O7 2 minus, and Cr2O7 2 minus is less than MnO4 1 minus. Comparison is there. How, again I am telling you, how would you account for the increasing oxidizing power? Increasing oxidizing power in the given series. Series is VO2 1 plus is less than Cr2O7 2 minus and is less than MnO4 1 minus. Then what is its explanation? Why it is like this? Why is this trend? Then this is due to the increasing stability of lower species, due to which they are reduced. Okay. And also you can calculate C VO2 plus 1 plus. Now what is the oxidation state of vanadium in this? Then you know oxygen is minus 2, then 2 oxygen is there, then minus 4, then V plus that is the minus 4 means it become V minus 4 is equal to 1 plus, okay, or plus 1. V plus VO2 means V minus 4 you can tell. V minus 4 is equal to 1 plus or plus 1. Then what is the V value? Then it become 5. In vanadium oxidation number is 5. Okay. And in Cr2O7 2 minus, what is the oxidation state of chromium? Then here Cr2 means 2Cr minus 14 is equal to minus 2, means 2Cr is equal to 12. Then Cr is equal to plus 6. Here chromium has plus 6 oxidation state, and in vanadium it is 4. Now here in MnO4, then Mn minus 8 is equal to minus 1, means Mn is equal to plus 7. Then for in case of vanadium it is 4. In case of chromium it is 6. In case of MnO4 1 minus it is 7. Oxidation number is now increasing, that is increasing oxidizing power. Then why it is like that? Then I told you this is due to increasing stability of lower species, to which they are reduced, means vanadiums are stable, plus 4 is stable, then plus 6 chromium, and this is stable, then manganese plus 7. Okay. Then this is the explanation. That question was, how would you account for the increasing oxidizing power in the series? In the series VO2 1 plus is less than Cr2O7 2 minus, and this is less than MnO4 1 minus. Okay. Then this is due to increasing stability of lower species, due to which they are reduced. Okay. Now I am going to discuss this chemical reactivity of transition elements. Transition metals vary widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve in mineral acid. Electropositive means basic nature. That's why it will dissolve in mineral acid. Although a few are noble, that is, they are unaffected by single acids. The metals of the first series, with the exception of copper is an exception, are relatively more reactive and are oxidized by 1m hydrogen ion or proton H+, though the actual rate at which these metals react with oxidizing agents like hydrogen ion is sometimes slow. Means rate is slow. Rate of reaction is slow. Again I am telling you, the metal of the first series, with the exception of copper, is relatively more reactive and are oxidized. This is oxidized by H plus. H plus means acid. 1M H plus. Though the actual rate at which these metals react with oxidizing agents like hydrogen means H plus, is sometimes slow. For example, titanium and vanadium in practice are passive to dilute non-oxidizing non-oxidizing acids at room temperature. The standard electrode potential value, means E value I am talking about, the standard electrode potential values for M2 plus to M2 plus bar M indicate a decreasing tendency to form divalent cation across the series. Correct? Decreasing tendency to form divalent cation across the series. This general trend towards less negative E electrode potential, I am talking about electrode potential. The general trend towards less negative electrode potential value is related to the increase in the sum of first and second ionization enthalpy. This is related to ionization enthalpy, first and second ionization enthalpy. It is interesting to note that electrode potential value for Mn, nickel and Zn are more negative. More negative means what? They are reactive. Okay, it is interesting to note that E values for manganese, for nickel and Zn are more negative than expected from general trend. Whereas the stability of a half-filled D cell, means D5 in Mn2 plus and completely filled D subcell, means D10 in Zn are related to E. E means electrode potential values. For nickel, electrode potential value is related to the highest negative enthalpy of hydration. Okay, for nickel, E value means electrode potential value is related to the highest negative enthalpy of hydration. An examination of electrode potential value for the redox couple, means M3 oblique M2 plus, means M3 is 3 plus is converting to M2 plus, means M3 has taken one electron and converted to M2 plus. Okay, then if we will examine the standard value for the redox couple M3 plus to M2 plus, shows that Mn3 plus, Mn manganese, Mn3 plus and cobalt 3 plus ions are the strongest oxidizing agent in aqueous solution. You remember it, question is asked. Mn3 plus and CO3 plus means cobalt ions are the strongest oxidizing agents in aqueous solution. The ions titanium 2 plus, vanadium 2 plus and chromium 2 plus are strong reducing agents. Titanium 2 plus, vanadium 2 plus, chromium 2 plus, they are reducing agent, a strong reducing agent. But Mn3 plus, CO3 plus are strongest oxidizing agents in aqueous solution. But titanium 2 plus, vanadium 2 plus and chromium 2 plus are strong reducing agents and will liberate hydrogen from dilute acid. Means 2Cr2 plus 2 hydrogen means 2H plus. It gives 2Cr3 plus, means chromium lost one electron, and plus H2 means 2H plus converted to H2. Again I am telling you 2Cr2 plus 2H plus. It is giving 2Cr3 plus H2 gas, means 2H plus converted to H2 gas. Correct? Means H plus reduced to H2. Okay. Now this one problem I am telling you that is asked in examination. For the first row transition metals, I am reading the question. For the first row transition metals, the E value means standard electrode potential, reduction potential. Always reduction potential means here I am telling it, and that is means standard reduction potential. Then that E value is given for metal 2, converting metal 2 to metal. Okay, M2 M2 plus is converting to metal. Then vanadium value is minus 1.18, chromium value is minus 0.91, manganese value is minus 1.18, ferrous value is minus 0.44. You remember it. In numericals, this value will be for solving numericals. This value is very important. You should remember. Ferrous minus 0.44, cobalt is minus 0.28, nickel is minus 0.25, and copper is plus 0.34. Correct? This value is given. Explain the irregularity in the above values. What is the irregularities? Then now value I am telling for vanadium is minus 1.18, chromium is less minus 0.91. Again Mn is the same as vanadium, means minus 1.18. Chromium is less minus 0.91, and after that ferrous is minus 0.44, means decreased. Cobalt further decreased minus 0.28, nickel further decreased 0.25, and copper is actually, if you will see the minus Mn onward, in minus value is decreasing. Manganese was minus 1.18 and ferrous is minus 0.44. Then in minus it is decreasing, but it is going towards positive. Minus 1.18, more negative. Ferrous is minus 0.44, less negative. Cobalt is minus 0.28, further less negative. Nickel is 0.25, further less negative, and copper is positive, plus 0.34. Then copper and ferrous value you should remember. Then explain the irregularities in the above values. That question is it is asking what are the irregularities. Then now I think you might be understood where is the irregularities. Now I am telling explanation. The standard electrode potential means M2 plus is converting to M. Okay, that is the reduction values. Then M2 plus oblique M values are not regular, which can be explained from the irregular variation of ionization enthalpy. Ionization enthalpy means first ionization and second ionization, delta H1 plus delta H2. Actually, these sum are related to electrode potential, don't forget. Then these M2 plus oblique M values are not regular, which can be explained from the irregular variation of ionization enthalpies and also the sublimation enthalpies, which are relatively much less for manganese and vanadium. Then for this irregularities, two main factors are there. First main factor is irregular variation. Irregular variation, this region I am telling you, that is the ionization enthalpy. First main region, why it is irregular, then ionization enthalpies, means sum of first ionization and second ionization enthalpy, first region, and second also the sublimation enthalpies. Sublimation enthalpy means sublimation energy. Sublimation, directly without converting to liquid, solid will go to the vapor phase. That time heat is liberated. That is called sublimation enthalpy. Then second reason is sublimation enthalpies, which are relatively much less for manganese and vanadium. That's why manganese and vanadium values are minus 1.18 and again minus 1.18. For both vanadium and manganese, same value, minus 1.18. Then this is actually irregularities, because otherwise if you will manganese value, if you will ignore, then you will find continuously that this value, electrode potential value is continuously that is becoming low negativity is becoming low, means minus 1.18. then chromium is minus 0.91. after that manganese is there, irregularity is here, then now just ignore this. After that minus 0.44, then minus 0.28, then minus 0.25, then it was increasing towards 34 regular way. Then irregularity was in manganese, minus 1.18. vanadium also same value. Then two reason is there. First is the ionization enthalpies, sum of the ionization enthalpies of first ionization and second ionization sum, and second is the sublimation enthalpies, which are relatively much less for manganese and vanadium. Okay. And other question I am telling you, that is also asked in examination. Why is the standard electrode potential value for the Mn3 plus oblique Mn2 plus, Mn3 plus to Mn2 plus couple much more positive than that for Cr3 plus oblique Cr2 plus or Fe3 plus oblique Fe2 plus? Okay. Why electrode potential E value for the Mn3 plus oblique Mn2 plus couple much more positive, Mn3 plus to Mn2 plus is much more positive than that of chromium 3 plus to chromium 2 plus or Fe3 plus to Fe2 plus. Okay, why it is so? Explain. Then now I am telling explanation. Much large third ionization energy of manganese, much larger you can say much larger third ionization energy of Mn, where the required change is from D5 to D4. Here too much ionization energy is required, is mainly responsible for this, because from d5, if you want to remove the electron, one electron, too much energy is required. Then this d5 to d4 requires too much energy. Okay, that is the main, you can say, main problem here, or you can say main reason for showing much more positive value is this removal of electron from d5, and it will convert to d4. Then d5 to d4 is mainly responsible for this. Okay, and this region also explains why the plus 3 state of Mn is of little importance. Mn 3 plus value is little importance. Okay, plus 3 value, because it is difficult to remove electron from d5 to d5 and to convert to d4. Okay, this I have told you. Now I am going to discuss magnetic properties of transition elements. Okay, these are very, very important magnetic properties. When a magnetic field is applied, listen carefully, when a magnetic field is applied to substances, mainly two types of magnetic behavior are observed. First, diamagnetism, and second, paramagnetism. Diamagnetic substances are repelled by the applied field, repulsion, while the paramagnetic properties are attracted. Substances which are attracted very strongly are said to be ferromagnetic. In fact, ferromagnetism is an extreme form of paramagnetism. Many of the transition metal ions are paramagnetic, means quickly can be magnetized. Paramagnetism arises from the presence of unpaired electrons. In d orbital, you know that unpaired electrons, generally it will be in d orbitals, unpaired electron may be. And paramagnetism arises from the presence of unpaired electrons. Each electron I am talking about, each such electrons having a magnetic moment, and magnetic moment is associated with first spin angular momentum and second orbital angular momentum. These two momentums are responsible for magnetic moment. For magnetic moment is due to first spin angular momentum and second due to orbital angular momentum. For the compounds of the first series of transition metals, the contribution of the orbital angular momentum is effectively quenched and hence is of no significance, no value. Okay, it means it is now when this orbital angular momentum value is now no significance in case of first series of transition metals. Then who is playing the main role for magnetic moment or magnetism? Then only a spin angular momentum. But in other series, that angular orbital angular momentum will play a role. But in first transition series, it has no role. Okay. For this I am talking about first series of transition metals. For this, the magnetic moment is determined. How much magnetism is there? Then you can tell by calculating the magnetic moment. Magnetic moment will tell about the magnetism, how much magnetic property is there. Then magnetic moment is determined by the number of unpaired electrons and is calculated by using a spin only formula. One formula is there because only it is applying for a spin, for a spin angular momentum. That's why formula name is called a spin only formula. And what is that formula? Then mu, actually magnetic moment, that is the mu. Then how will you calculate the mu? Then mu is equal to, means magnetic moment is equal to under root n, and in bracket n plus 2. Again I am telling mu is equal to under bracket under root n, and in bracket n plus 2, where n is the number of unpaired electrons. N is the number of unpaired electrons and mu is the magnetic moments. And what is the unit of magnetic moment? Then its unit is, or it is measured in Bohr magneton, Bm. Bohr, B-O-H-R, Bohr magneton, Bm. A single unpaired electron has a magnetic moment of 1.73 Bohr magnetons, means Bm. When n value is 1, then in formula you would put the value of n, then n outside under root n, then 1 in the place of n you put 1, then you will get n is equal to 1, inside n plus 2, then 1 plus 2, 3, okay, then under root 3, then what is the square root of 3? That is the 1.73. Like that we can calculate what if by putting the value of n, if it is 2, if it is 3, correct, if it is a 2, then in bracket it will be 2 plus 2, 4, and outside 2, then 4 into 2, 8, then a square root of 8, that will be the value of mu. Like that way, for 3, n is equal to 3, n is equal to 4, you can calculate. Thus, the observed magnetic moment gives a useful indication. What is the value of, what is the importance of mu? Mu will calculate. And what will it tell? Then it will tell, it is very, very useful, okay, that it will give, magnetic moment gives a useful indication about the number of unpaired electrons present in the atom. If you are knowing the value of mu, then you can understand how many unpaired electrons are there in an atom or molecule or ion. The magnetic moments calculated from the spin only formula and those derived experimentally for some ions of the first row transition elements, I will tell you, okay. Then this calculated and observed magnetic moments value I will tell you. The experimental data are mainly for hydrated ions in solution or in the solid state. I will compare both value, okay, calculated and observed. Calculated means theoretical value and observed, what you got actually. Then these experimental data are mainly for hydrated ions, means these ions are with water in solution or in the solid state. Then now scandium. First I will tell the ions and then I will tell the configuration and then how many unpaired electrons are there. Then what are the calculated value and observed value, magnetic moment value I will tell. Then scandium 3 plus, in this, in 3D no electron is there, 3D 0, means n is equal to 0, number of unpaired electron is 0. Then if you put the n value, n is equal to 0 in the formula, then you will get only 0, correct. Then calculated value is 0, observed value is also 0. But in titanium 3 plus, titanium 3 plus, now in 3D 1 electron is there, n is equal to 1, 3D 1. Then if n is equal to 1, then if you put the value 1, n is equal to 1 in formula, you will get 1.73. This is actually calculated, theoretical, but experimentally it is found 1.75, roughly same 0.02 difference. And titanium 2 plus, in this case 2 electrons are there, D2, 3D2. 3D2 means n is equal to 2. Then if you put the formula n is equal to 2, if you put in the formula, you will get calculated value 2.84. But observed value is less, slightly less, 2.76. Like that way, vanadium 2 plus, 3D value is 3, means n is equal to 3. Then after putting the value n is equal to 3, you will get calculated value 3.87, and observed value is very close, 3.86. Chromium 2 plus, means here 3D4 is there, n is equal to 4. Then calculated value is 4.9, and observed value is 4.8. Little difference is there, 0.10 difference is there. Manganese 2 plus, Mn 2 plus, means 3D5, n is equal to 5. Then calculated value is 5.92, and here observed value is 5.96, very close. Okay, only n value you have to put in the formula. Now Fe2 plus, now 3D6 is there. Okay, then here in 3D6 unpaired, but here unpaired electron is only 4 because 2 are paired. D6, you know that these things after 5, 1, 1, 1, D5 are there. Then first it will fill unpaired 1, 1 and single, and then after that it will become paired. Then 6th electron means what will happen? It will go to the first d orbital, and then now 4 are unpaired and 2 are paired. Out of 6 electron, 2 are paired. First orbitals are paired and rest 4 are unpaired. Out of 5, 4 are unpaired and 1 orbital is paired. Then here this n is equal to 4. You should be careful in this way. Only unpaired you have to count. Then many d orbitals are there, 5 d orbitals are there. Then now first d xy orbital is have 2 electrons, and rest 4 are 1, 1. Hence unpaired electron is 4. Then now in this case you will get 4.90. This is the theoretical or calculated, but observed value is between 5.3 and 5.5. Like that way, cobalt 2 plus. Then now 3D7. Then now again you can understand here unpaired electron will be only 3 because 7. After the 5 it is going to be paired. Then now only n is equal to 3. Out of 7, now 2 are paired. 2 orbitals are paired, 3 are unpaired. Then n is equal to 3. Always you should be careful. Only unpaired you have to count, not the paired. Then out of 5 orbitals, first 2 beginner orbitals are paired, 3 are unpaired. N is equal to 3. When n is equal to 3, then calculated value 3.87, but observed value was found 4.4 to 5.2. Like that way, nickel is 3D8. Then now see one more d orbital paired. Then now only 2 are remaining unpaired. N is equal to 2. When n is equal to 2, then calculated value is 2.84. But observed value is 2.9 to between 2.9 to 3.4. Okay, experimental value. Observed value means experimental value, and theoretical value means calculated. Theoretical both are same, or experiment or observed both are same. Now come to the copper 2 plus. Then copper 2 plus means D9. Then D9 means what? Now 4 orbitals are paired, only 1 are unpaired, means n is equal to 1. Then now theoretical value is 1.73 and experimental value is between 1.8 to 2.2. Well, somewhat close. And Zn is Zn2 plus, zinc 2 plus, means it is the D10. The D10 means unpaired electron is 0, n is 0. Then theoretical is 0 and this also 0. Okay. Then this I have discussed about the magnetic moment. Magnetic moment will tell about the magnetism, how much value for magnetism, and with the knowing the when you will come to know the magnetic moment value, then you will get idea that in that atom or molecule or ion how many unpaired electrons are there. Okay, this is the importance of magnetic moment. Now simple question is there it is asked in examination. Calculate the magnetic moment of a divalent ion. Divalent ion in aqueous solution of its atomic number is, if its atomic number is 25, atomic number is 25 and it is a divalent. You have to calculate the magnetic moment of a divalent ion in aqueous solution if its atomic number is 25. Then it is very easy. You yourself can solve it. You have to only think, you have to write the electronic configuration, and you see the last orbit in D. In D, how many electrons are unpaired? But question is that it is a divalent, means whatever this is there, means you have to 25, atomic number is 25, then you have to write electronic configuration for 25 minus 2, 23, because divalent means plus 2 plus, means 2 electron gone, then only for 23 you have to write. Then if you write the electronic configuration, explanation I am telling you, with atomic number 25, the divalent ion in aqueous solution will have D5 configuration. D5 configuration means 5 unpaired electrons. The magnetic moment mu is now mu is equal to under root 5 in bracket 5 plus 2, means 5 plus 2 7, 7 into 5 35, then 35, what is the square root of 35, then it will be around 6, 36. For the 36 it is 6, then for it is 37, it will come around that only. Then exact value, if you take a square root of 37, you will get 5.92. Okay, 35, 5 plus 2 7, 7 into 5 35. For 36 exact 6, but for 35 it is 5.92 bm. Okay, Bohr magneton. This I have told about the magnetic properties, and question is asked. Okay, now I am telling you about the this formation of colored ions. Formation of colored ions. This is very, very interesting. Already I have told you, and again I am telling you. This is the right place to tell the formation of colored ions. When an electron from a lower energy d orbital is excited to higher energy d orbitals, the energy of excitation corresponds to the frequency of light absorbed. This frequency generally lies in the visible region. The colored observed correspond to the complementary color of the light absorbed. Complementary color of the light absorbed means after light suppose falls on the matter, okay, after that, after absorbing some light, rest light will come out. Then what is the wavelength of this reflected light? Okay, because some light material will absorb. Then now you can understand. The color observed corresponds to the complementary color of the light absorbed. The frequency of the light absorbed is determined. The frequency of the light absorbed is determined by the nature of the ligands. Ligand is responsible for the frequency of the light absorbed, because different type of ligands are there. Maybe H2O. H2O is a ligand. Okay, NH3 is a ligand. Cl, chloride ion, bromide ion, iodide ion, these are fluoride ion, these are the example of ligands. In aqueous solution, where water molecules are the ligands, the colors of the ions observed are, I will tell you different colors. Okay, I will tell these details, I will tell the colored, but you have to remember. Now I am telling you few colored solution of D block elements. Okay, this you have to remember. First row transition metal ions in aqueous solution. I am telling you in reference of aqueous solution, from left to right. Okay, means vanadium to, starting from vanadium to copper. Then now I will start scandium also. Scandium from left to right complete. Then scandium 3 plus. 3 plus means 3d0. In d orbital no electron is there. When no electron is there, then there is no transfer of d electron. D is equal to 0. No electron is there, then there will be no transfer of electron. Means scandium 3 plus and titanium 4 plus. No electron is there in d orbital, d0. That's why both are colorless. Scandium 3 plus, titanium 4 plus is colorless. Now 3d1, one electron is there. Now a scope is there for transition from one d orbital to the other d orbital. A scope is there. Then titanium 3 plus means 3d1. Then in this case color will be purple. Ion will show purple color, purple. And V4, vanadium 4 plus also has 3d1 configuration. Then this is blue. Okay, actually size also matters. Finally, actually which type of this frequency they are observing, that decides the color. Other factor is also there. That's why little variation you will find in color also. Means if you see the spectrum, then you will see that all lights are overlapping to each other. Slowly and slowly they are changing. As for example, blue and violet. Blue and violet both will be close. Okay. Then minor change will be there in color. Then vanadium V4 is 3D1. Okay. Vanadium V4 is 3D1. It is a blue color, and vanadium 3 plus, it is a 3D2. Then now it is a green color. Okay. Then actually what happens now, S also may be there. After the 3D, S is there. Then from the S also will require some energy to, if it goes outside. For that part, some reasoning, due to this region, some can say energy change will be there. Okay, energy change will be there. That's why it is not only for 3D. Sometimes it will include S also. Okay, that's why color variation is there. Then this thing for vanadium V3 plus 3D2, it is a green. You remember it all. And again 3D3, vanadium 2 plus means 3D3, then it is the violet color. And chromium 3 plus, this is also 3D3, it is also violet. And manganese 3, Mn3 plus 3D, this is coming under 3D4, then this is the violet. Okay, then now you are seeing that you are considering mainly d electrons in d orbitals, mainly that is the responsible for colored. Okay, because these d orbitals, and they require less among themselves, and dd transition, what we are telling, for that they require, I can say, less energy means frequency will be not too much difference. Then now chromium 2 plus is 3D4, this is a blue, it looks blue. Now manganese 2 plus, this is 3D5, then it is the pink color. Ferrous 3 plus, it's also 3D5, but it is yellow. But here you are observing that these elements are differing. Correct? The number of atomic number is differing. Always that also you remember. Atomic number is also differing. But you are considering, main consideration you are doing for only 3D. Okay. Maybe other orbitals also. Due to that, some energy they are also using. Okay. Then I told you about the ferrous 3D5. Ferrous 3 plus D3D5, it is a yellow color. And manganese 2 plus, Mn2 plus, it is a 3D5. Manganese Mn2 plus is 3D5. It is a pink color. See how colorful ions are there. Colorful ions. Pink color is due to Mn2 plus. Okay, and it is a 3D5. And iron, I told you, Ap3 plus 3D5 is there. Many 3D5s are there, but despite that, color change is there. But all are colorful, that is sure. Okay, then Ap3 plus 3D5, it is a yellow color. Now ferrous 2 plus, Ap3 plus is yellow and Ap2 plus is green. Remember it. In lab you will find the salt, yellow salt also, green also. Then Ap3 plus ferric, that is the yellow, and ferrous Ap2 plus, that is 3D6, that is the green. And cobalt 3 plus and cobalt 2 plus means 3d6 and 3d7. 3d6 is cobalt 3 plus and 3d7 is a cobalt 2 plus. Cobalt 3 plus and cobalt 2 plus. Both are blue pink color. Very good. Blue pink. CO3 plus, CO2 plus. Okay. Nickel 2 plus is green. Ferrous 2 plus is also green. Nickel 2 plus is also green. And now Cu2 plus is a 3d9. Cu2 plus. This is also blue. Also you remember it is a blue. Question is asked. Cu2 plus. Okay. And Zn2 plus. This is a D10. No, there is no scope for transition. That's why it is a colorless. Colorless. Then today I am stopping only here. Next class I will continue with formation of complex compounds, catalytic properties, formation of interstitial compounds, alloy formation, all things I will discuss in the next class. Thank you.